Hello, my name is Zdybał, and today I wanted to talk to you about our novel method to select a subset of the thermochemical state vector for reduced order modeling in such a way that we get an improved low-dimensional manifold topology when projecting the state vector to a lower dimensional space as opposed to projecting the full state vector. But first I wanted to start with a bigger picture. So increasingly in combustion we are dealing with big datasets that are high dimensional. We represent those datasets with a matrix X, and the columns of that matrix are different thermochemical state variables such as temperature, pressure, chemical composition, so that matrix then represents our state vector. But because of the many chemical species involved in chemical mechanisms, these datasets can be highly dimensional. But reduced order models leverage the fact that very often in those high dimensional datasets we have some strong low dimensional structures, and the reduced order models aim at finding those structures and representing the dataset with a smaller number of parameters. So we start with our original dataset X, and we project it to a lower dimensional space where our dataset is now represented with this new parameters eta. And this gives us a chance to achieve dimensionality reduction and can give us some benefits in modeling combustion processes. So that's great, but projecting those high dimensional datasets to lower dimensional spaces can actually introduce some problems. Now, to give you a visual example of what those problems can look like, I will start with this toy dataset that is a three-dimensional dataset basically generated from some Gaussian functions. And we can basically create infinitely many two-dimensional projections of this 3D dataset. And one projection that I can create is by looking at that dataset directly from top to bottom and projecting it onto a plane of sight. And if I create such a projection, that it might look something like this. So this original three-dimensional dataset is now represented in 2 dimensions by this new parameters eta1, eta2. But maybe if I looked at my dataset at a little bit of an angle to the z-axis, then I might see something like this. So now if I zoom in on a particular region on that first top projection, then basically because I created that dataset on a uniform XY grid, I'm going to see a very nice grid, unique grid of points. But an analogous region on that second projection can look like this. So you can see that there's this overlap of observations that happened on that projection. And that overlap can be problematic in, for instance, building some regression models on top of such a projection. So if we now try to build a model that, given some set of parameters eta1, eta2, would predict some dependent variable, then it might not have problems predicting some dependent variable on that unique projection. But on that second projection, there are some regions where if we ask the model what is the function value at that location, the model might not really know which value to predict. So because of that non-uniqueness, the model might not really know should it predict the dark blue color or the light blue or the lightest blue. So there is a need to quantify all of those topological behaviors that happen on manifolds. And we have come up with a cost function that I'm going to denote with this fancy L letter that allows us to perform quantitative assessments of manifold quality for reduced order modeling purposes. So to give you the intuition of how we build that cost function, I will start with a two-dimensional projections, two-dimensional manifold coming from a combustion dataset. And this particular projection also suffers from that overlap problem. So there are some regions on that projection where if we try to build a model, the model would not really know which value to predict. And the starting point for building our cost function is the work done by Elizabeth Armstrong and James Sutherland. They proposed this metric, this d hat metric, for characterizing manifold qualities. And basically what this metric does, how it is constructed, is we scan that manifold for any variation in the dependent variable values at different length scales. So if my dependent variable in this case is that blue color that colors the manifold, then I can scan that manifold at those biggest length scales denoted by sigma. And if I see some variation in the dependent variable at those length scales, then they will manifest themselves as that rightmost peak in this d hat metric profile. Now, I can zoom in on that manifold further and start scanning it at those scales. And if I still see some variation at those scales, and in this case I still do because there's this non-uniqueness problem, then that will manifest itself as that peak further to the left for smaller length scales. And I can basically keep going. I can scan the manifold at even smaller length scales. If I still see some variation at those length scales, then they will manifest themselves as that leftmost peak. So constructing this d hat curve is the first step towards building our cost function, and then there are two more ingredients. So the first one is we multiply that function by some penalty function, which now returns this dashed black curve. And what you can see happened here is that we first penalize multiple scales of variation that happen in that d hat profile. So especially the variation that happened at the smallest length scales got significantly amplified. And we wanted to amplify that because that can be particularly linked to non-uniqueness. And there's a second characteristic to that penalty function, which is that we reward large feature sizes. So the location of that rightmost peak conveys the largest feature sizes on the manifold, and we want to have those feature sizes as big as possible, since that would in principle enhance reduced order modeling. And the second step is to compute the area under that curve. And that area now becomes our cost function, which turns manifold topology into a single number. So we get a single number for a manifold topology for a given dependent variable. So what can we use our cost function for? Well, often the different challenges with low-dimensional manifolds have been mitigated in the literature through appropriate data preprocessing. The most straightforward way of data preprocessing is data scaling. So we basically multiply every state variable by some scaling factor. The second approach would be variable selection. So we take our original matrix and we discard certain columns from that matrix and project that new subset instead of the full data set. So to give you a hint of how much a manifold topology can improve with appropriate data preprocessing, here I have a two-dimensional projection, again of a combustion data set. And there are two characteristics that I wanted to point out here. So first, this projection is colored by temperature. And you can see that the region of high temperature creates a very small, very narrow feature on that manifold. There is also that non-uniqueness. So the low temperature region got curled into a very small region on the manifold, and that got overlapped with even high temperature values observations. But then if we find a way to improve that projection through appropriately preprocessing my dataset, then I can, for instance, see something like this. So what you can see here is first that high temperature region is now increased. It occupies a larger portion of the manifold, and we've been able to reduce non-uniqueness associated with those low temperature regions. There is still some non-uniqueness that remains along the edge of that manifold, so there is still some room for improvement. And our cost function pays attention to those two characteristics that I mentioned. So first of all, it penalizes small feature sizes. It will see that and it will penalize that. And it penalizes non-uniqueness. So if I compute my cost function for that first more problematic projection, then this is the number that I get. And if I compute it for this improved projection, then I get a smaller number. So I get a smaller cost for a better manifold topology. And in this case, I computed the cost from a couple of dependent variables, and I took a cumulative sum over a number of important dependent variables. So the way that I got from this problematic projection to this improved projection was through variable selection. And in this work, we have created an algorithm that performs that subset selection based on our cost function. So it is optimizing based on our cost function. So to give you a hint of how that algorithm can be implemented, if this is our starting state vector, x, composed of temperature and a couple of species mass fractions, then if I project this state vector as it is, then this is the projection that I get. And now the algorithm basically removes every variable one at a time. It's removing it, creating a projection, and measuring the cost of that resulting projection. And eventually it removes that variable for which the cost was smallest. So at the first iteration, it decides to remove HO2 mass fraction, and this is the resulting projection. So you can already see that some of that non-uniqueness have been alleviated. And the way that the algorithm selected that HO2 mass fraction was through minimizing the cost function. So for that, removing that variable reduced the cost the most. And that's why it was removed. At the next iteration, it decides to remove HCO mass fraction, and this is the resulting projection. You can now see that this high temperature region is increased. At the next iteration, it removes O mass fraction. This is the resulting projection. And then H2O mass fraction. This is the resulting projection. And then basically the algorithm keeps going. But the reason why I stopped here is that once all of the iterations have passed, the algorithm goes back and checks for which of the manifold topologies the cost was smallest. And in this case, it was that topology. So the algorithm will return the subset which created that projection. Now we have observed that performing the subset selection can bring benefits compared to just scaling the data. So here I'm showing costs on the y-axis for various projections of the same data set, but pre-processed with different scaling techniques. So on the x-axis, you can see different scaling techniques. And you can see that some scaling techniques, such as the 0-to-1 scaling, result in high costs. So those are not good choices for that particular data set. But if on top of scaling the data, I also perform an appropriate subset selection with our algorithm, then these are the costs that I get. So you can see that the costs now dropped for all of those scaling techniques if I also select an appropriate state vector subset. Now the ultimate goal of this is that we improve the reduced order models, which often incorporate nonlinear regression. So to go back to the figure that I showed you earlier, if there is any way in which we can improve those problematic characteristics that happen on manifold and help regression not have to make those choices, which value should I predict, then that's a big win for us. So here I'm showing the errors from regression, from kernel regression of a couple of variables. So the first three variables, these SZ1, SZ2, SZ3, those are projected source terms. They are highly nonlinear functions of the state variables, and then I have the state variables, so temperature and species mass fractions. And you can see that the highest errors happened for these three source terms, which are highly nonlinear functions of the state variables. And these errors are for projecting the full state vector, but with the best scaling option already selected. But if on top of selecting the best scaling option, I also select an appropriate subset optimized with our cost function, then these are the errors that I get. So you can see that for many variables, the errors dropped, especially they dropped for these three highly nonlinear variables. You can also see that for some variables, the error actually increased. And with our cost function approach, we can select dependent variables which we want the algorithm to pay attention to. And in this case, I didn't, for instance, select HO2 and HCO mass fractions. So the algorithm had no way of paying attention to those variables specifically, which is probably why the errors are higher. So more generally, we have observed across a couple of fuels that we tested that there is a correlation between what our cost function tells us and the regression performance. So on these three plots, you can see on the x-axis the cost, on the y-axis the errors from kernel regression, and the gray points are randomly generated subsets of the state vector. We generated sufficiently many subsets so that we can see some trends emerging on those scatter plots. With the black dot, I mark the full state vector, and with the red triangle, I mark the optimized subset, which came from our subset selection algorithm. So you can see that generally, lower costs result in lower regression errors. You can also see that the cost for the optimized subset is smaller than the cost for the full state vector, and also smaller than any of the random subsets costs. And with the exception of ethylene, you can also see that regression errors are smaller for the optimized subset than for the full state vector. And what I should mention here is that regression techniques alone require tuning for a particular problem. So we have hopes that combining our manifold improvement strategies with later improving the regression performance, we can get further benefits beyond what we report in this work. So to summarize, in this work, we've built tools to help construct better reduced order models. We have implemented all of our tools, so the cost function and the subset selection algorithm, in our Python library, PCEfold, which is open source. You can head to the documentation and see the instructions on installing the software. And you can also find many illustrative tutorials. And with this, I thank you very much. I'll be happy to answer your questions. And the last thing I wanted to mention is that as I'm approaching the end of my PhD, I'm currently looking for postdoc opportunities in reduced order modeling and in manifold methods applied to complex systems. So I'll be happy to discuss any opportunities with you. Thank you.